I guess you give the person a bonus mark.
Sorry, I didn't get it, but maybe I'll start, okay? So, so we are after this theorem here. So if a prime plus something divides k1 plus k2, then either the prime divides k1 and the remainder is split. Well, we stated it already. I'm not sure I want to state it again. But the proof is a bit difficult, and it involves a lot of R3 intuition, three-dimensional intuition, and three-dimensional theorems which are far from obvious. And we kind of started the class all wrong to prove this, because more or less, you know, on the first class I said I don't care about the precise definition of a knot. Here's what it really is, and here it actually matters, okay? And a few other details about knots actually matter. So I decided to give a class on a bit about three-dimensional intuitions, those couple of theorems that we missed. I only intend to state them, not to prove them, but then, you know, to show that they're delicate, you have to show the kind of near counterexamples, and the near counterexamples are various funny things that happen in R3. So I want to, so really what I want to do is a class that could have been the first class of the year about funny things that happen in R3, and by the end of the hour I'll hope we'll get a sufficient feel for R3 to actually tackle the theorem. Okay? So, yeah, so my real goal for today is get a feel for funny and not so funny, I mean funny and also normal R3, okay? So let's start. So I actually would like to start with a handout that I prepared for an algebraic topology class that I gave in 2001, or maybe it was 2002. So just various funny pathologies in R3. So first of all, an interval can be noted, right? Our intuition. So you know, I'm going through funny things which are not necessary for the proof, not all necessary for the proof that we have at hand. But if I'm going through funny things that are necessary, I'm also putting in a few that are not necessary. This is irrelevant, okay? But still, a continuous interval in R3, a continuously embedded interval in R3, may be noted, or may be not equivalent to a standardly embedded interval. So this is not equivalent, sorry, I mean the notation here means, maybe I'll write it like that. This is equivalent and this is not equivalent to just a standard interval in R3. So why? Basically the complement of a standard interval is simply connected, but a complement of the complement of a picture like this is not simply connected. So if you look at the little red loop here, then if you try to push it out of this funny infinite knot, you have to make it, you have to push it, and it goes smaller and smaller and smaller as you go through the iterations, and eventually, well, at some point it must meet the knot at its end point. Yet this set, or that one equally well, is homeomorphic to an interval, continuously homeomorphic to an interval. And it's an embedding, right? I mean, I could prove all of these facts, but I think it's visible, okay? So that's funny fact number one. However, for smooth things, it cannot happen. Here is funny, but that requires a proof. So this is just to indicate that these proofs are non-trivial, right? Because, okay, they make a distinction between smooth and continuous. Here's another funny example. So let me explain what you see here. So what you see here is a loop, okay, which in itself is a part of a loop of loops. So here is another beginning of a loop, but it continues this way, and here is another beginning of a loop here is another beginning of a loop which continues this way, and those big loops make a chain which closes on itself. So somewhere up above my screen, and you can see it, those, so basically you get a chain of loops which makes an even bigger loop, but it's linked, okay? Now, each of these loops, so the big loop that I indicated first is actually made out of a chain of smaller loops. This one, and then that one, and then that one, I hope you can see it, and so on. And they make the same pattern. And each of the smaller loops is in itself a chain of even smaller loops. Okay? And the picture is not of high enough resolution, or in fact was not rendered sufficiently well, but each of the tiny loops is in itself a ring, is in itself made as a ring of smaller loops, which in themselves are so on. Okay? So this set is an embedding of the Cantor set into R3. Okay, as topologically it's just a Cantor set, because basically to make it I took a circle and then I embed, so really a thickened circle, so a solid torus, and then I replace it by a ring of rings, so I really took its intersection with a ring of rings, and then within each ring I took its intersection with a ring of smaller rings. So it's analogous to the construction of the Cantor set, and in fact you can show that it is homeomorphic to the Cantor set. Yet the fundamental group of the complement is not trivial, because if you take a path that goes, basically that links with this, so a path that goes like this, you cannot undo it. Okay? So even a Cantor set can be knotted in R3. Okay. Next funny thing. Oh, gee, I forgot the funny thing that was right above this funny thing which is kind of hidden. So this I think we did talk about. So in the continuous world there are no knots. Okay? So in other words, you could think that you could define knots by saying a knot is a continuous embedding of a line into R3 modulo continuous deformations of such things, but that fails because you know, if you make I'm showing the failure on an example, but right, if you make a trefoil, you can pull it really tight, and in the limit, the trefoil, the knotted business, becomes tiny, 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 and at some point, and you just continue pulling it until it becomes a single point, and this is a continuous process. Again, you have to visualize it, think about it. It's a continuous process. It's not a smooth process. Okay. So there are no, so we have to be working in the smooth category if we want to talk about knot theory. Here's the next funny example. So there is the Jordan curve theorem. The Jordan curve theorem says that if you have a circle in the plane, so I will state it again later, but if you have a circle in the plane and it can be, and it has to be, and all it has to be is continuous. So if you have a continuous circle in the plane, it divides the plane into two connected components, each of which is homeomorphic to a disk. I suppose the internal one is a disk and the external one is a disk with a point removed, or if you think about it in the sphere, then both of them are disks. Okay? That's not true in R3, or for spheres in R3. So here is the so-called Alexander Horn sphere. So here's how you do it. You start from a sphere. Here is an ordinary sphere. And you pull out two horns out of it. So, with the horns pointing into each other. Okay? But then the ends of the horn are like, I suppose it's better if you make them not sharp like here, but like a bit of flat, like the ends of my hands right now. And then what you do is, out of each end, you pull out two smaller horns that are kind of interlinked as here, and then you have two meeting of horns, new meetings of horns that are created here and here. But they don't quite meet, you keep them a little bit apart. And then at each end here you construct two little horns that interlock. And you keep going this way, and at the end you get this picture. Okay? And you keep going to infinity. Now this is a continuous process. Again, you have to think about it a little bit and understand it. But basically, the modifications that I make are modifications in smaller and smaller parts of the parameter space. So, the big parameter space of the sphere is a sphere, and the first modification is made in two little disks where I pull the horns. Now, within these horns, I make further modifications in tiny, tiny, smaller disks. And then I keep making modifications in smaller and smaller things. And these modifications are smaller and smaller. And at the end, you get this came out like a funny smiley face by chance. But anyway, it's at the end, this is a continuous embedding of S2 into R3. Okay? And it's an embedding because, points that, you have to go through it. Maybe, again, it's not clear I want to go through the pathology more than to show that it exists. So there isn't a Jordan theorem for continuous S2s in R3. However, this is not smooth. Okay? So let's continue. Oh, that's the end. But I do want to say what there is. So, yet, there is the Jordan curve theorem, the standard Jordan curve theorem. Yet, so in R2, the Jordan curve theorem actually does hold. So if gamma is a closed, continuous, simple, so not self-intersecting, meaning embedded, loop, then R2, you know what, maybe I'll be sophisticated and write it as S2, then S2 minus gamma has two connected components, both homeomorphic to disks, so to two-dimensional balls, to B2s. Okay? As you know, it's a non-trivial theorem.
May I ask a question?
Sure.
So with the in 3D, is it not the fact that the sphere has its inside and the outside for the Jordan-Kerr theorem?
Well, but the inside, actually spheres, continuous spheres still divide R3 into inside and outside. So this sphere does have an inside and does have an outside. And in fact, the inside of this sphere is a ball. But the outside of this sphere is not a ball, because if you look at a path that goes like this, so basically a loop that wraps around one of these horns, there is no way to disconnect it. Because to disconnect it, back in the first picture, so back here, you could disconnect it by, so the same loop, you could disconnect it by just pushing it and then pulling it out through the gap. Here, you could still disconnect it. You'd have to push it, but you'll have to deform it in a funny way in order to pull it out through the gap. You'd have to, it's a bit hard to describe, but you can, here in every finite stage you can still pull it through the gap. But in order to pull it through the gap, it has to pass through these tinier and tinier passages, and in the limit, its distance from the S2 has to go smaller and smaller and smaller, and then in the limit it has to be 0, which means that it's not a homotopy in the complement. So the complement of this, so the outside region of this S2 in R3 is not in S3 is not a ball. By the way, can you make a sphere such that neither its interior nor its exterior will be balls?
Just do the same thing on the inside. You make holes.
Yeah, just do the same. Just do the same towards the inside. So instead of building horns, think of this as if it's made of some nice membrane, and push your hands into it. So you push your hands in and kind of create anti-horns into the inside, and then, so first you push your hands, and you push your fingers, and you push your fingers, and so on. Okay? Yeah, so in R3, the complement of a continuous sphere need not be a ball. Yet, there is the, so one reason why I said it is to emphasize that the following theorem, the Alexander-Schoenflies theorem, is non-trivial. So it says that a smooth S2 in S3 divides S3, in other words, the complement has two connected components into two components, each equivalent diffeomorphic, each diffeomorphic to a ball. Now, if you want a proof of this, well, it will take us too far aside, but I'll tell you where the best proof is. So, the second best proof is in a book by Ellen Hatcher. So, so the second best proof is in a book by Ellen Hatcher. I hope I spelled it correctly. It's the same guy that our core algebraic topology class often uses his book. But the book is called, so it's not really a book, it's a book project that he aborted and never finished. But it's still on his website, and I forget the name of the book, but it's something like 3 manifolds. Something about 3 manifolds. So this is the second best proof. And the best proof, so a few years ago I had a summer student, Calder Morton Ferguson. You may have heard, you may even know him, some of you. And the project I suggested to him was to rewrite Hatcher's book by adding lots and lots and lots and lots of pictures and animations. So he got from Ellen Hatcher, he got the original tech, so he re-teched everything, adding, I mean, seeing that it was an aborted project, it sort of was okay with Hatcher. So he got the original tech and annotated it and added lots and lots and lots of pictures and some animations, so movies of how things move within the proof. Okay? So if you want to see the best proof, you go to my website and then you go to the students subsection and then you go to Morton Ferguson, and then there is a link to whatever he did. Okay? Good. So what else did I have to say? So here are a few corollaries. So corollaries of the Alexander Schoenflies theorem. So one, there are so actually maybe it's just one corollary, sorry. There are no noted S2s, so spheres, in S3. You cannot note a sphere. Or in other words, if S is an S2 in R3, so an embedded S2 in R3, and if S prime is the equatorial, sorry, not in R3, in S3, the equatorial S2 of R3, so basically the equator, then the pair S3 with the first sphere is equivalent to the pair S3 with the equator, with the standard sphere, I could have taken any other sphere, not necessarily the equatorial. And what I mean by what I mean by that these two are equivalent is that there is sorry, and this is in the smooth, no noted smooth. And what I mean by that is that there is a diffeomorphism phi of this to that, which takes this to that. Okay? So roughly, how do you prove it? So suppose you have a crazy S2 suppose you have a crazy S2 in S3. Well, this isn't crazy, but you know, crazy as you wish. Since its inside is a smooth ball, you can contract it to a smaller and smaller thing until at the neighborhood of a point it will simply be a tiny ball. And you can contract this thing while carrying points of R3 with you, of S3 with you. While pulling, while stretching points of S3 with you. Maybe I will not show. But so at the end it is equivalent to a tiny ball, to a tiny sphere, and a tiny sphere is equivalent to a big sphere. Okay. So that's the corollary. However, so yet there are noted tori in, so tori means S1 cross S1, or also called T2, in I don't know, I write S3, but when I write S3 I mean R3 with a point at infinity. Okay, so can you tell me how?
Question.
Yeah.
So about S2 that cannot be noted. So just like we saw above the horn, if we pull two sides and then maybe knot it and then cut open some small portions and do a connected sum, is that not knotting?
Say it again, I didn't understand. If what?
I mean we pull two horns out of the sphere.
Yeah.
And make some loops and knot it and maybe
so there is
some
no
two things and do a connected sum. Is that not knotting?
There is no finite way, right? So the horn sphere was created by a limiting process. There is no finite way to knot two smooth horns, because, well, you know, two smooth horns are just basically, there is no way to knot something without, intuitively at least, without closing it without closing it at the end, because if it's not yet closed, you can pull it back. So if you just take a sphere and pull out two horns, again, I mean, I can, you know, take a sphere and pull out two horns, then you can pull them back in. At least in the smooth world you can. It requires a proof. But in the smooth world you can.
Yeah, what I meant is, so you tie it and then do a connected sum. That's what I mean.
But then it's, so you mean you want to actually, let's see, where do I have space? Oh, actually I have space above. Well, maybe I went too far. So you mean, sorry. You mean, let's take a ball with two, and take two horns out, and then just connect them somehow. but then it's not a sphere anymore. Okay, I want the parameter space to remain a sphere. In fact, you've just explained how to make a knotted torus. But in fact, how to make a knot... Oops, sorry, that was a mistake. I wanted to scroll. So in fact, how to make a torus is kind of obvious. You just... right, so if you want to find a knotted torus in R3, well, you just take a knot and look at its tubular neighborhood. So in fact, here is a knotted torus in R3. I mean, if you think of this thing that I drew here as a line, sorry, if you think of this thing as a line, then it's a knot. If you think of it as a tube, which actually it is, then it's a knotted torus. So by the way, this is a knotted torus whose inside, so, okay, sorry, a knotted torus, a torus still will divide R3 into an inside and an outside. So maybe I'll write it. A T2 in S3 still, sorry, and let's make it smooth. In fact, even if it's not smooth, but the smooth T2 in R3 still divides R3 into, sorry, oh actually I do want it to be R3 this time, into two connected components. One which contains infinity and one which doesn't contain infinity. So one containing infinity, and I will call it the outside, and the other one, and one that doesn't, and I will call it the inside. So for the torus shown here, the inside is a standard inside of a torus. Topologically, the inside is just a, so in our case, in this example, so if you look at the tubular neighborhood of a knot, so if you look at the tubular neighborhood of a knot, so you turn it into a tube, wrong. Sorry, if you turn it into a tube, then the inside is a standard solid torus, meaning a two-dimensional disk cross an S1. When I say standard, I mean homeomorphic, is homeomorphic to this. But the outside is not homeomorphic to B2 cross S1. How do I know it, by the way? Well, for example, we computed the fundamental group of the complement of the outside and it wasn't trivial. Okay? How do I know it's not trivial, by the way? I mean, we wrote a bunch of we wrote a bunch of relations, but the word problem in groups is notoriously complicated. So maybe the group we wrote is the trivial group at the end of the day. How do I know it isn't? Well, it has...
Abelianization?
What?
You do abelianization?
No, the abelianization will actually be, sorry, not trivial, will be Z. will be, so when I say trivial, I mean equivalent to the fundamental group of this, which is Z. The abelianization will actually be Z, always. But we also counted how many representations this group has into the dihedral group of order 6, sorry, the D6. And that was equivalent to the number of 3 colorings. And so we counted 3 colorings and, well, okay. So anyway, can you imagine the opposite? So can you think of a torus in R3 whose inside is non-trivial, but whose outside is trivial?
You just think of it as being in S3 and then move the point at infinity?
Yeah, you just move infinity to here, right? You just, correct, you just moved infinity to here. But here's what it looks like. And I want to draw it because we will in a minute use it for something else. So it looks like the following. You, for example, you can take, here's a way of drawing it. You can take a box in R3, and then you can draw a knot within that box. What have I done? No, sorry. You can draw a knot within that box. And then drill a hole around this box, around this knot. Well, it's a bit hard to draw. So basically, I just took my funny twisted drill and drilled a hole around this knot. And then my surface will be the tube union the box. So, you know, if this was made of wood, it's all the exposed parts of the wood. Then the outside is just the big outside ball union a tube, the missing tube. I suppose it's the Tim tube. Sorry. And the inside is the complement of a knot. So the inside now is non-trivial. So here is a theorem which we will not use, but still not use for the theorem we care about, but still worth knowing. So you can never do both. So if T is a smooth T2 in S3, then at one of the sides, and either the inside or the outside or both is standard. So is B2 cross S1. We actually don't need it. I'm just stating it for fun. Oh, I wanted to say a few more things. Gee, this is. I thought I'd have time to start the proof, but I'm spending too much time on the little things. So, sorry. What do I do? So yeah, okay. I wanted to say, so at the beginning of the class I didn't want to define knots, but now I want to give you 4 definitions. So there are 4 equivalent definitions of a knot in R3. So for the first 3, you take a smooth curve in R3. So a smooth curve in R3 modulo either one of the following three relations, three possibilities, three equivalence relations. So equivalence now, a smooth simple curve, non-embedded curve in R3, modulo either one of the following. So first one is smooth homotopies of such. The second possibility is so-called ambient isotopies. So ambient means including the ambience, not just the knot itself. So in this definition, or in this second definition, you say that gamma 1 is equivalent to gamma 2 if there exists a family H sub T of diffeomorphisms of R3, so of diffeomorphism invertible. Wait, does the word diffeomorphism include the word invertible? I think so. Yeah, okay, so of diffeomorphisms such that H0 is just the identity map, and H1, you know, I should have called them gamma 0 and gamma 1. So H1 takes gamma 0 to gamma 1. So in other words, if you look at H1 and you compose it with gamma 1, you get gamma 0. So in pictures, it means that not only you're deforming the knot, you're deforming all of R3 with it. So not only you're deforming this, you're also deforming the ambient space. Okay? Definition 3. So definition 3, equivalent relation 3. So basically, you don't even need the t's in between 0 and 1. So you say that gamma 0 is equivalent to gamma 1 if there exists a single isotopy, H, a single diffeomorphism, H, so a single H, such that H carries gamma 1 into gamma 0. So basically, well, and then the last definition is planar curves. So planar curves modulo the Reidemeister moves. So a non-trivial theorem is that these are all equivalent. And the reason I'm stating it now is because up until now we only cared about definition number 4, but now we will care about definition number 3. Yes, there was a question. Yeah.
Shouldn't we require, in definition C there, shouldn't we require H to be orientation preserving?
Oh, yes, we should. Thank you. Otherwise, a knot is equivalent to its mirror image. So let me add it. Let me add it here. Orientation preserving diffeomorphism. Sorry, you're right. Okay.
Question about the ambient isotopy. Does that also have to be smooth, or is the fact that we're transforming all of R3 allow us to just work with continuous ones?
I'd rather simply say everything in the smooth world. I'm not sure. I think continuous is enough, but I'm not sure. Okay? There are actually definitions of knots in the continuous category, but then you have to say a little bit more about what happens near the knot. So okay? Okay. So by the way, so what is a prime knot? So definition. So a knot. So gamma is prime if whenever in S2 S, so whenever a specifically embedded sphere S intersects gamma exactly twice, then one of the sides is trivial. And I say, sorry, a gamma is prime if, I keep forgetting the small details, if it is non-trivial, yet if anything that intersects it, if whenever you find something that intersects it twice, then one of the sides is trivial. So let me draw a picture, and this is annoying because I really wanted to do the nicer picture, but I doubt I will have time for it. So here is a curve gamma, and so actually it should continue, and when I say one of the sides is trivial, I mean, so here is a sphere, so this is the sphere. If you remove the sphere, you no longer have a knot, neither on the inside nor on the outside. However, you can shortcut the sphere. So you can go along the boundary of the sphere from one of the 2 points of intersection to the other of the 2 points of intersection, and then if you take the inside of the sphere and shortcut the outside, then this is a non-trivial knot. However, in this case, if you look at the outside and shortcut the inside, this is a non-trivial knot. This is a trivial knot. Okay, so one of the sides was trivial. I wanted to show you one funny example of where it's a bit confusing. Where is which side is the trivial side? Let me try to do it really quickly. So okay, so let me start from a trefoil knot, okay, and make a tube around it, make a tube around, draw a tube around it. I'll be a second pastime. So here is a tube around it, but instead of going with the tube all the way down, I will close the tube down here. So here the tube gets sealed. And then on the outside, I will also close it like that. So this is a sphere, because all I did was I took a, so and now let me complete it this way. So the green stuff is an S2, because all I did was I took one sphere and I put my finger inside it and twisted my finger somehow, and but didn't get all the way down to the other end. So my question here is, which side is trivial? So the inside of this S2, right, this is an S2, the inside component is a tiny interval, absolutely straight. The outside is a big messy thing. So which side is trivial?
Wait, isn't this a torus? Like it's a cylinder.
No, it isn't. This sphere, this finger that I've put in, did not go all the way through. Okay, I've stopped pushing a little bit. So this is an actual, the two intersection points are here and here. And the interval between the two intersection points on the inside sphere is a straight line. So my question is which of the two is trivial? The inside ball with the part of gamma which is here, or the outside ball with the part of gamma which is all the rest.
Are we allowed to deform the disc around the outside?
Sorry, you're allowed to do everything that math allows. I mean, I thought here is a sphere in R3, and here is a curve that intersects it twice. Okay, so there are two knots that you can get out of it, the inside and the outside. And the question is, which of the two is trivial?
The outside one is trivial?
Yeah, the outside one is trivial.
Yeah.
Right. The inside one is a tiny interval, but the sphere itself is knotted. So if I were to, by the definition, if I were to shortcut along the boundary of the sphere, I'll get out of gamma, well, the shortcut goes like this. To shortcut from this intersection point to that intersection point, I have to do this blue curve. And if I take the inside interval, namely gamma 1, union the shortcut, I get a knot. But if I take the outside, namely gamma 2, using and then the blue shortcut, so I really get so I get this red thing. It goes all the way through and then back, so you can pull it out, and at the end it's unknotted. So yeah, I'm way over time. So this one is trivial, and this one is non-trivial. And the reason I'm showing this is that it will be hard to understand this when we talk about this very same shape will appear tomorrow, not tomorrow, on Friday. Okay. Good. So,
A question.
yeah.
So I don't see. So where you have the hole, is that also not counted as outside? Because I'm not quite. clear on this.
So again, the green surface is an S2. The green surface is an S2 because I took a sphere and I pushed my finger in it. It never changed the topology. So basically I get a tube which is sealed on one end, connected to the outside of a sphere. This green thing is a sphere. Once it's a sphere, it has an inside and an outside. By Schoenfliess's.
I mean, pushing your hand into a balloon, right?
Yeah.
So if you push your hand into a balloon, what surrounds your hand is still the outside, right?
Yes. Your finger never crosses through the balloon. When you put your hand into a balloon, your finger never crosses through it, so it's always on the outside. But basically, the definition is by, topology, by connected components. So, if you have a point here so this is infinity, and if you have a point inside the tube, well, they are in the same connected component because there is a path. And if you have a point here inside the ball, then they're not on the same connected component because you have to cross the sphere to get out. So I mean, it's not my arbitrary decrees which say which is inside and which is outside. It's the definitions. We are way over time, 6.5 minutes. I'll disconnect the video and